Okay, this is a set of review problems of increasing difficulty. Correlates with the material that we would have learned in Chapter 3 of Brown, 10th edition. It's a white textbook. This is our textbook. If there are any questions you would like me to address, you can send me a note and I will address those questions. None of these questions come from the textbook. I just made these ones up, but they're along the same lines of what you'll find in Chapter 3. The first question is calculate the molar mass of copper sulfate pentahydrate. Pentahydrate means that the crystal itself contains 5 water molecules. So it's not a wet substance. It looks completely dry, and it forms triclinic, blue triclinic crystals. And if you subject it to about 120-degree temperature, it will dry the water off, and the crystal will turn from a royal blue color to a baby blue powder. So it breaks down the crystal. Drying it off, driving the water off out of the crystal will destroy its structure. So the first question is calculate the molar mass. And what we do is we add molar mass of every one of the constituent elements, and we get 249.686, which I then report to 5 significant figures because these two numbers are only containing 5 significant figures. The next question is calculate the percent by mass of sulfur and water in the above compound. So I started by calculating the percent sulfur. 32.066 is the molar mass of sulfur. This is the molar mass of the whole molecule. I multiply that value by 100. And the result is 12.8425%. I rounded off to 5 significant figures again, so the answer is 12.843% sulfur. In the next part of the question, we're calculating the water content. So here's the water content of the molecule. Here's the 5 oxygen atoms. Here's the 10 hydrogen atoms. Divided by the molar mass of the molecule times 100, and we get 36%. The third question is something I obtained from the Merck Index, 11th edition. It says that lycopene is a substance that occurs in ripe tomatoes. It is a brightly colored substance because it has many double bonds conjugated with single bonds, which makes substances reflect visible light. Its percent composition is 89.48% carbon and 10.51% hydrogen, and it has a molecular mass of 536.85. That's the information I got from the Merck Index. Now, what is its empirical formula and its molecular formula? The first step is to turn those percentages into gram values by assuming a 100 gram amount. We divide by the molar mass of each one of the elements involved. In this case, only carbon and hydrogen. We get these two mole ratios. We divide by the smallest of the two numbers. And the result is 1 to 1.3996. Now, some students are tempted at this point to round this off to 1.4. And you might get away with it if you do it and you won't get a wrong answer, but I don't recommend that you round off anything until the calculation is done. The next step is to find an integer value that when you multiply both of these numbers by, it will result in something very close to an integer value as a result, because we can't have half an atom in a molecule. So it turns out that when you multiply these two numbers by 5, this turns into 5, and this 1.399 times 5 gives you 6.998, which is very close to 7. So the empirical formula of this molecule is C5H7. That's what I have recorded here. Empirical formula equals C5H7. I symbolize empirical formula by EF. Then the next step was to find out how many times heavier the real molecule is compared to the empirical formula weight. So I did that here. The molecular mass is 536.85. That was given in the question. And the empirical formula weight is found out by multiplying each of the constituent atoms by the numbers that we found for the empirical formula. So it gives you an empirical formula weight of 67 grams per mole. Remember, the empirical formula is like the molecular formula in lowest terms. So if the actual formula, for example, of glucose has a formula C6H12O6, therefore the empirical formula of glucose is the lowest form of 6,12,6, which is C1H2O1. So we find that the ratio between the molecular mass and the empirical formula weight is very close to 8. So what we're going to do is multiply the empirical formula, C5H7, by 8, getting the real formula of lycopene, which is C40H56. So the formula of lycopene is C40H56. The fourth question asks, a 25-gram sample of propanol is burned, and I demonstrate here 3 different ways of showing the structure of propanol. This is the bond line notation. This is showing the actual methyl groups and methylene groups with an alcohol on the end of it, and this is just showing how many atoms are involved in the molecule. This is the one we're going to use. It makes the calculation a little bit easier because we can visualize how many atoms are involved. I just remind you that in any calculation requiring stoichiometry, you're going to start, say, from grams, go to moles. From moles, you go through the stoichiometry, and then from moles, you go to grams again. You always have to go through that pathway, because how do you equate grams with grams? They have different molar masses, so you have to go to moles. Every one of these types of calculations, you have to go to moles. So you go through to moles by, if you're starting with grams, you divide by the molar mass, you get the number of moles of one substance, and how do we equate it to the number of moles of another substance within the same equation? You have to have a balanced equation, first of all, and then you use the stoichiometric coefficients to convert the values. And that's what we did here. We showed the combustion of propanol. Remember, propanol requires oxygen to burn like everything else. And any hydrocarbon will release carbon dioxide and water when it's combusted. This is the balanced equation. So we're going to find out how many moles of propanol. 25 grams of propanol divided by the molar mass of propanol. See here, this is the mass of carbon. Here's the mass of hydrogen. Here's the mass of oxygen. We get...
Excuse the interruption, would teachers please dismiss members of the junior girls basketball team. They are to meet in Moen Hall by 1:30. All junior girls basketball team, please meet in Moen Hall by 1:30.
This gives us the number of moles of propanol, 0.416. Then we go through the stoichiometric coefficients for the amount of moles of CO2 formed versus the amount of moles of propanol used is 6 to 2. So we write those stoichiometric coefficients here. How do we know which way it is whether it's 6 over 2 or 2 over 6? Well, we're trying to eliminate propanol. And propanol is the numerator here, so it has to be the denominator there. And the answer is going to be moles of CO2. And then from moles of CO2, we multiply by the molar mass of CO2, which gives us 54.9 grams of CO2. We're only allowed 4 significant figures according to the equation, because we start off with 25.00. So here's our final answer for the number of grams of carbon dioxide. The same calculation is repeated to find out how much water there is. We start off by finding how many moles of propanol, so we just start off with this number. But then we multiply by the stoichiometric coefficients for water and propanol instead of CO2 and propanol. So now it's 8 to 2. And then we multiply by the molar mass of water to find out how many grams of water, and we report it to the correct number of significant figures, in this case 29.98. The fifth question asks, aluminum reacts with hydrochloric acid to form aluminum chloride. If 50 grams of aluminum is reacted with 50 grams of hydrochloric acid, how much aluminum chloride is formed? What is the limiting reactant? How much excess of the other substance is left? Now, in this calculation, we're starting off with 50 grams of each one of the involved substances, and we're going to have to determine what the limiting reactant is. Excuse me for the ruckus, but now you can see a bit more clearly. So we start off by dividing by the molar mass of each one of the elements. 50 grams divided by 26.98 for the aluminum. 50 grams for the hydrochloric acid divided by the molar mass of hydrochloric acid. We find out we have 1.85 moles of aluminum, 1.37 moles of hydrochloric acid. Notice how I keep all my decimal places. I don't round off, that way I don't have to worry about rounding error. I only round off my final answer. I just keep all the numbers in my calculator when I'm doing the calculation. So we see that there are fewer moles of hydrochloric acid than there are moles of aluminum. So that means the hydrochloric acid is going to finish first. Even if it was a 1-to-1 ratio, the hydrochloric acid would finish first. But in fact, for every 2 moles of aluminum, you need 6 moles of hydrochloric acid. So now the hydrochloric acid is being used at a rate 3 times faster than than the aluminum. So the moles of hydrochloric acid being used are 3 times as many moles of hydrochloric acid is being used for every mole of aluminum being used. So that means this stuff is going to finish off even faster than if it was 1-to-1. And this is definitely the limiting reagent. And that's what I say over here. So we're going to start our calculation with the thing that's going to finish first, the hydrochloric acid. So 1.37 moles of hydrochloric acid times the stoichiometric ratio for this reaction. We notice how we use the balance reaction. These numbers are coming from these coefficients next to the molecules. And we're getting that 2 moles of aluminum chloride is forming for every 6 moles of hydrochloric acid that is consumed. So that's going to tell us how many moles of aluminum chloride is going to form, because the moles of HCl is going to cancel. These two things will cancel. And that's going to give us an answer in moles of aluminum chloride. And then we multiply by the molar mass of aluminum chloride. Here's the molar mass of aluminum. Here's the molar mass of chlorine times 3. And we find out that there's 60.95 grams of aluminum chloride. It comes out to 61.0 grams when we account for significant figures, because I only had 3 in the original question. And then it says also what is the limiting, how much excess of the other substance is left. So this is how many moles of hydrochloric acid there was. Here is the stoichiometric ratio for the consumption of hydrochloric acid and aluminum, which means this much aluminum is used in moles. But we start off with this much aluminum, so if we subtract this number from the amount that we start off with, we're going to find out how much aluminum is left. So 1.396 moles of aluminum is left. To be perfectly consistent, we're going to say we're only allowed 3 significant figures, so it's going to be 1.40 moles of aluminum.